Yes, one more. Welcome. So so like I was saying, this is a two-part lecture. So unfortunately, it could go 2 hours. So if you need to leave, that's fine. We're recording these, and we'll do part one, and then we'll take a break because I think we'll probably all need a break, and then we'll do part two. These are basically just general topics about how to debug programs. Mainly focused on the things you have to do for CS24, but it's there's a lot of general material in here that will carry up over to whatever programs you have to work on, professionally or in research groups or whatever, and regardless of the language as well. So like I say here, debugging is a skill that you pretty much need all the time when you're programming because you always make mistakes when you write programs. I think in all the years, I've been writing programs for a long time, since I was about 13 years old. And I'm a little older than 13. And I think in all that time, I've probably written 2 or 3 programs that were absolutely bug-free on the first time. So that's like not a lot. So pretty much you always need to be able to debug your programs. Now, CS24 in particular you need this for because the systems are really, really complicated. I mean, any kind of computing system type problem is going to involve a lot of different details that you need to keep track of. So debugging becomes extremely important. The other thing too is that, well, now that CS2 actually does a little bit of Java and a little bit of C and a little C++, you've been exposed to programs that compile into a binary file that you then run, and you can't necessarily open it up and peer into it very easily. But this may still be, for some people, the first class where you have to debug a binary program without having an interpreter to be able to poke at it and see exactly what's going on. So like I say, even though the tools are confusing for digging into things, you still need to learn them so that you can save yourself a lot of time. Okay. And I mentioned this already. I know I mentioned this in the first lecture too, but if you know how to debug well, then you're going to cut off hours on your programming assignments for CS24 and for other classes. And definitely, if you end up programming for a living, again, that skill is going to serve you really well. I have a friend named Pete who's an incredible debugger, and I mean he has other skills as well, but he is absolutely unique in being able to track down, bugs in programs, and I'm always amazed at how good he is at it. So he's, everybody that he works with is just always impressed by that. Okay, so these 2 lectures that I put together are basically focused on trying to impart as much information as I can to you about debugging without you actually having the experience. So hopefully it'll give you some framework in which you can, begin to attack programming issues in a little bit more intelligent way. Like I say here, there's a lot of stuff that you need to think about when you're a software professional as well. And this is not the point of these lectures. These are really to help you debug your programs, that you write for classes and things like that. So there's 2 parts. The first part is basically how do I think about programs with bugs and how do I go about finding the causes of those bugs. And it is mostly independent of the specific language, although we will have some C-specific material in here. And then the second part, which will also be about an hour, is what tools and approaches can you use to specifically debug C programs. Okay, and also IA32. So this is more CS24 specific. And we'll talk about GDB, and we'll also talk about another tool called Valgrind, which is very, very powerful. Okay. So the question that we're going to start off with is, what is a bug in the first place? And I've mentioned this again in class. The easiest way to think about a bug is actually as being 2 things going together. Okay. The first thing is that you have a defect. You misprocess information in some way in your program. You don't make the right logical decision in your program, or you compute the wrong value, something like that. Now that defect, at the point that the defect occurs, now you've got invalid state in your program, which over time is going to cause your program to do more and more erroneous things. Okay? And so at some point, you actually can observe the manifestation of that defect, which you see as a failure. Your program crashes, you get an NaN as an answer as opposed to a real value or something like that. So you see some way in which it fails. Now, like I say here, it's not always necessary for a defect to manifest. It may be on a particular code path that only triggers in certain circumstances. One of my favorite bugs of all time was actually a compiler bug that I read about in a book. The compiler would crash on Wednesdays. nobody could understand why it would only crash on Wednesdays, and every time the compiler would crash, they would send an email to the company that wrote the compiler saying, your compiler crashed. And the company would try to figure it out, and they'd say, well, we can't reproduce it, so we can't explain it. Next Wednesday would roll around and the compiler would break again. Well, the problem was they had a little string buffer in there that held the day of the week. Wednesday happens to be the longest day of the week. And it overflowed by a byte and wrote over something else and the program crashed. But then they didn't see that because they would get the bug report and try to fix it on Thursday. So you have situations where bugs don't necessarily manifest in all circumstances, and that's frustrating because you can't always necessarily diagnose what's the cause of an issue. Also, you have situations where defects don't necessarily show up right away. I had a very frustrating bug that I was trying to figure out where my program would run for about a month, and then it would basically hang. And we would all scratch our heads and restart it, and then I would start it again, and it would run for about a month and then hang. And we couldn't figure out what it was. And if we, restarted it every 3 weeks, it wouldn't hang. And obviously, if you let it run longer, it would just stay hung. So those kinds of things are very difficult sometimes to track down and figure out what they are. I may talk about that bug a little bit later because it was an interesting one to figure out the cause of. So if you have a defect and then you have the manifestation of the defect, you can imagine that all you can observe is the manifestation, and you have to figure out the actual defect from just the manifestation and various other things that you try to do to diagnose the issue. So once you identify the issue, though, it usually is pretty easy to fix, but the difficulty is figuring out the cause of the manifestation that you see. Now, you also have what are called design bugs or design issues, and sometimes those are much more expensive to actually fix. Where you have a wrong approach to a problem and you don't realize it until you hit some special case that you didn't realize you needed to handle. I'm not going to spend too much time talking about that. By and large, we give you the right approach for problems when we give you homework assignments and things like that. But design issues are very, very challenging. Sometimes you have to redesign a very large part of a system. Yeah, so the whole point of this is that the defect is just the cause of the failure, but it's not the thing that you actually observe, and so you have to sort of figure out, what is the actual origin of that issue. And like I say, the bigger the separation between the actual manifestation and the actual cause of the issue, the harder it is to figure out what's causing it. Okay, so sometimes you have a situation where the defect causes it right away. That's awesome, right? You have you try to dereference a null pointer or something like that, and your program crashes. Then it's usually really easy to figure out how to fix that kind of bug really easily because the defect and the manifestation are right next to each other. Okay, but yeah, usually that's not the case. So here's a really simple example, the kind of thing that strikes fear in most programmers' hearts. You have one function that goes and manipulates a linked list, and unfortunately, it has a defect in it, so it mangles the linked list. But it still thinks that it completes properly. Okay, so F1 completes successfully, at least it says it does. And then F2 comes along and tries to use the linked list that's now been mangled, and F2 crashes. And so you think, aha, the bug is in F2, but really it's not. Okay. Bugs like this are pretty difficult to track down. You have to really do some sleuthing to figure out exactly what's going on. Okay. So yeah, here's the question. How do we actually determine the cause of the failure? So we're going to be spending some time talking about that in this first talk. Now, probably the most common approach for trying to preemptively identify defects, software defects, is using assertions. I mean, how many people have used assertions here? Yeah, like just about everybody uses them now. It's really great. I'm really happy that CS1 promotes the use of assertions. I hope the CS2 does. We certainly promote it in our CS11 tracks. And the more extensively you use assertions, the easier it is to become aware when your program actually has a software defect, because an assertion will fail, something like that. So like I say, you have conditions you expect to be true, you explicitly state them in an assertion, and if they happen to not be true, your program will be stopped, and you'll be told, hey, this assertion wasn't true, and you can go look at what the cause might be. So that's a really good approach. In C, if you're not already familiar with this, you just include assert.h and then put the assertion into your code with the assert statement. Okay. The nice thing is you can compile these out, so you don't have to leave them in. You don't have to worry about them being, slowing down your program or anything like that, because eventually you can just compile them all out. Okay. So like I said, you can use them to check function arguments, return values, state managed by your functions. You can use them to diagnose flow control issues. There's a lot of ways that you can use assertions, and hopefully we use them extensively enough in the CS24 code that we give you that you'll see plenty of good examples of this. But use them yourself, and you'll definitely benefit. Unfortunately, there's one place you can't use them. That's IA32 assembly code. It's not really easy to do that. Wouldn't it be nice? Maybe somebody can get on that. Okay, but anyway, let's say that you have a failure that you've observed. One of the students that contacted me over the weekend said, my allocator fails and it's crashing in malloc. Okay? Now remember, I actually talked about that a little bit on Wednesday and Friday. The program that you write is myalloc and myfree, but his was crashing in malloc. So now you have a mystery to solve, and you have to think about, okay, what is the actual cause of this crash that I'm seeing? Okay? So there is one good thing that no good detective ever does, and I've gotten a lot of answers over the years when I ask this question. What do good detectives never do? But the answer that I'm looking for is detectives that are good don't guess randomly, right? They don't just sort of close their eyes and point and say, you did it. Because that would be wrong. That would be dumb. They actually follow some logical process of reasoning. There is a programming version of this malady, which is that when you have a program that's not behaving correctly, you go in and you just sort of scan through it and look at stuff that you think might be the issue, and you just change it. And you don't really think about, does this actually relate to the manifestation of this defect that I'm seeing? Is it related? Or anything like that. You just start changing stuff. Okay, this usually happens with students that are very tired and homework that's due shortly, and it's just like, I'll just change whatever I can to try to see if I can get it to work. Okay, that's known in various circles as a shotgun approach, and Mike in particular likes to call it monkeys on a typewriter. And yeah, the results are usually terrible when people try to do this kind of thing. So you really need to actually think through what is the manifestation and track down the defect itself from the indications you see. Okay? And then once you have a really good bead on it, that's when you try to make the fix and see if the problem has gone away. Okay? And so like it says here, you hunt bugs with a rifle, not a shotgun. Okay? You want to take them out that way. Oh yeah, and there's another little thing. You're not as likely to introduce other defects. Programmers do this a lot. They're called regressions, where you have working code and you try to fix a bug, and some of the working code stops working because you actually introduced new issues. Those make you very sad. Okay, so before you can do anything else, when you have a defect in your program, you have to figure out a way of reproducing it. Okay? And like I say here, you recreate the steps that cause the program to fail. This is the kind of stuff, if you need help from me or your TAs, it's really good to be able to express this to us. Because if you just say my program crashes, we're going to say, well, I'm sorry, but we won't really be able to help you because we won't know what it was you were doing that made it crash. Okay, so like I say here, was it data inputs? Was there some specific data that you give it that causes it to crash? Or a specific interaction with the program that causes it to crash? Okay, you have to think about these kinds of circumstances. And like I say here, there's three reasons why you need to be able to reproduce the failure. The first one is so that you can actually watch it as it fails. That helps you figure out exactly where in the program the defect actually is. Like I say, you can see exactly what the program was doing as it crashed. The second one is so you can zero in on the cause. Because if you see that the program is failing sometimes, but not other times, depending on the input or depending on what day of the week you run it or things like that, that actually will tell you and give you clues as to what part of the code the defect might actually be in. Also, if you can reproduce the failure and you make a change and the failure goes away, yay, you can sleep. You can turn in your assignment, right? You fixed it. Okay, so these are the reasons why you need to be able to reproduce the failure. So this is always the first thing that good programmers do when they're faced with a buggy program, is they try to figure out in what specific circumstances can I cause this to fail reliably. This is also why it's really hard to debug concurrent programming issues, because a lot of times those things are intermittent failures and they become much more difficult to reproduce in those circumstances. Okay, so question, which of these reasons actually requires debugging tools? Yeah.
Number 2.
Well, it's really kind of number 1, right? So you can actually watch it as it's failing. Okay? So you need to be able to peer into the program state as it's running to figure this out. Okay, like it says here, so that you can see where your programs are failing or where they were when they failed, which is another very useful thing. Some of you may already be familiar with this, but I'll show you how to use GDB to find out exactly where your program was when it crashes. Okay. Like I say here, it's a small part of debugging. A lot of debugging is mainly thinking about what am I observing and how does it relate to the code that I wrote or that some lame person wrote, right? But it is still very important to be able to peer into the way that your program is executing. Okay. Now, one thing that the first time I read this, I thought it was really corny, but then every time I've applied it, it's really shortened my debugging efforts, is actually keeping a log as you try to diagnose an issue. Okay, like I say here, general description of the failure, inputs or circumstances in which the failure occurs. It's also helpful to keep track of inputs in which it does not occur, because that helps you remember the things that made it not happen. Also, ideas of potential causes, along with the efforts you made to verify your ideas. Okay? Now, you may say, well, this is kind of cheesy sounding, but in fact, every company that has large software projects does this, except they do it online through a bug tracking system. Okay, everybody's supposed to be able to record what they did to try to diagnose or reproduce or fix a bug, and then everybody can share that information that's tackling a particular bug. Now, you can also do this on a piece of paper by hand, which I've done several times, and like I said, it's really helped me zero in on a problem very quickly. Okay? So yeah, it helps you focus. And also, the nice thing about this is that if you have a log going, and you're like, okay, you know what, it's 3:30 in the morning, it's really time for me to sleep, you can put it aside and then come back another time and actually look at it again. So that also by itself is a huge asset. Because like I say here, if you're trying to debug things when you're tired, you are not going to think very clearly. Okay? In fact, I remember there was one time that I was working at a company where I had been programming for like I carpooled with this guy out to Westwood, so it was about a 3-hour round trip every day. It was pretty lame, traffic is horrible here. And so we get there about 9, and I was a software engineer, and he was a manager, so I programmed all day. And then at 6 o'clock, we were ready to go home, and they ran into some really subtle concurrency issue on the clustered version of our product. I'd written the clustering part, so it was my code, it was my responsibility, and so I was the one who needed to fix it. Now, my manager buddy was like, well, if you really love this company, you'll stay and try to fix this code. And I'm like, you know what? I really love this company, so I'm going to go home and rest and then fix it tomorrow. And they weren't very happy with that. And we tried to fight with it for about 45 minutes or an hour, didn't get anywhere. And then I said, you know what, this is dumb, I'm going home. And then the next day I came in and fixed it within about 10 minutes. And the QA manager watching all this said, it was so beautiful to watch you work. So he was Persian, very passionate guy. So he'd say very funny things like that all the time. But anyway, I mean, it's those kinds of things. If you attack a problem with a fresh mind, you're going to get through it really quickly. So make sure that you keep a debug log when you have more challenging issues, because I promise you it will help you get through your bugs more quickly. Okay, so you've been able to reproduce the failure. Like I say, your program fails, and you know how to make it fail every time. So the problem is that the defect is probably only just a small handful of lines. And so you need to find those lines of code. And so now you need to go about the process of isolating the failure. Okay? You try to find the smallest possible way to get the failure to occur, because the smaller you can narrow it down, the smaller the code is that's actually executing before the defect occurs. So like I said, the less code that's involved, the easier it is to find the defect. Okay? So let's say you had a program, and you have some giant log files. Now, these are not giant log files, actually. They're relatively small. 27 megabytes. Okay? That product that I worked on with the clustering concurrency bug would regularly process like 2 gigabyte, a bunch of 2 gigabyte data files every day that were generated by AOL. So 27 megabytes is teeny compared to that. But let's say that you generally work, but then there's one log file. You've been told, hey, this log file makes your program crash. So what do you do?
Try and see what's different about it.
Yeah, you need to figure out what's different about it. So obviously the first thing that you would want to do is probably find that log file, right? Get the operations guys to give you the log file or whatever it is, so that you can actually try it. Okay, so let's say you get the log file and you can reproduce the issue. The only problem is 27 megabytes is still a lot of data to process and probably a lot of code that's being executed in the process of churning through that data. So you need to actually narrow in on the cause of that bug. So one option is to sort of do a binary search in the log file. Well, I'll take the first half and feed the first half to the program. And if that crashes, then I know the problem's in the first half of the data. Or maybe it's the second half. And you can narrow in, maybe there's a few specific lines of the log file that cause it to crash. I've had that happen, where there was some unexpected character, like a non-ASCII character that appeared in the log data, and I didn't even expect that it was going to be there. Okay? And like I said, the log files are very large, so you just sort of cut them down until you find the specific lines that are causing the problems. Okay? So if you're lucky, that's what you find. And then the bug becomes really easy to fix because now you can figure out exactly what piece of code is choking on that data. Now, you may also have a situation where that doesn't help. Okay? So the issue does not get reproduced by trying different parts of the log file. Okay? So now you have to think to yourself, okay, what's different about that circumstance that might cause my program to behave differently? Yeah?
You could try a different random log file of the same size.
Yeah, you could try different files of the same size. Maybe it's a memory issue. Maybe there's some issue with the amount of memory required to process this log file. There may be some issue with the combination of values in this log file that causes an issue to occur. I mean, the point is that, well, you've learned something by trying to cut down the log file into smaller pieces. But now you have a slightly more challenging debugging issue because, well, now it may actually be, that log file or some characteristic of the log file as a whole. Okay? So things like this is a lot more difficult to try to work through, but at least you've learned something as you've been trying to isolate the issue. Okay? So like I say here, you learn more about the nature of the defect as you go through this process. That's why it's really frustrating when we see programmers throw their hands up in the air trying to, or they give up really quickly on trying to diagnose an issue because they're actually cutting themselves off from learning more about what the actual cause of the issue might be. Whatever you learn is going to be helpful because then you can share that with other people. And I don't know, I'm really curious how many people in here have done the whole trick of, you have a problem in your code and you just can't figure it out, and then you go over to a buddy to try to get their help, and you start explaining the issue, and a third of the way through you realize what the problem is. Yeah, I've done that a lot. People have done that a lot. It's just funny that way. So the more that you try to study and isolate a defect, the more you're going to learn about what it possibly could be and also what it can't possibly be. That's really important. Okay, so yeah, the previous example was trying to isolate the input. So we have 27 megabyte log file. We presume that it's something about the file causing the failure. Okay, but you could also try to isolate the code in several different ways. Like I say here, memory allocator from assignment 3. I'm sure nobody's allocator has crashed on them yet, right? Mine crashed the first time I ran it. Okay. So yeah, you run the allocator using the testing program and it crashes, and it does that every time. So hey, I can reproduce it, right? The only problem is the testing program doesn't have inputs that I can control. So what do you do about this situation? This is where it gets a little bit more challenging. Okay. So like I say here, another important thing to do when you're trying to debug a program is you have to make sure that you really understand the system that you're trying to debug. Okay? So question, what are the major functional components of the program? Okay? And what portions of the code map to each one of those major functional components? So I have, what are the major parts of an allocator? What are the operations that an allocator performs? There's two of them, right? Alloc and free, right? So those are not necessarily implemented by the exact same code. So you can sort of have a guess, well, if I'm seeing a failure here, what it might correspond to. Okay, so like I say here, what major functional components and what portions of the code correspond to those functional units. Okay? So yeah, if the failure manifests when a specific feature is used, at least you know where to start looking, right? Also, are there portions of the code that is always executed? Okay? If you have a failure and it's manifesting all the time, no matter what you're doing, it's probably in common code. Okay? Now, if you have a failure that's occurring only sometimes, then the likelihood that it's in common code is much less, because you know it's always executing. And, well, it's executing and the failure doesn't occur, and it's executing and the failure does occur. Okay? Here's another really good one. Are there portions of the code that you can disable or remove and then run the test again? Okay. When students have allocator issues, this is frequently where I start in trying to help them debug their allocator issues. Okay. Like I say, if you can remove part of the code and the failure still happens, well, I learned something, right? It's not in the code I removed, because that's not there anymore and it's still happening. Okay. So yeah, you can ask the same questions about the inputs. Are there specific portions of the code that execute only on certain data inputs, okay, or sequences of inputs? So if that's the case, then you can try to correlate the inputs that are causing the failure with the portions of your program that may contain the defect. Okay? And I don't know if anybody in here has taken the C++ track of CS11, but the sparse vector is always the classic example that we use for this, because you have a linked list of elements, you have to keep it in sorted order by index, and my test code feeds in specific sequences of elements so that you can target the testing a little bit more specifically. So there's a test that adds values with decreasing index. So that's always inserting values at the beginning. Make sure that code works. Add values with increasing indexes. That always tacks them on the end. So you make sure that code works. Okay? Add values sort of randomly. Well, that's going to test the code that inserts in the middle of the list. So you can see how you can target tests if you understand your system to focus on different portions of the code. Okay? And if you see one of these tests fail and another one doesn't, then that tells you, well, that's probably where the failure is actually occurring. So that's where the defect would actually be in the code. Does it make sense to everybody? It's like really important to be able to understand what parts of your program correlate with what kinds of data inputs or what kinds of user input, things like that. Okay. So the whole point is that you're performing experiments. You know, it's just like physics, it's just like chemistry, any science where you do experiments. You're doing experiments with your program, which you thought you understood, but evidently not, right? And so you want to try to understand what is the nature of the defect that you're observing. So you need to correlate the behaviors you observe with the program's source code. Okay, and yeah, like I say, the more effective you are at doing this, the faster you're going to zero in on bugs. All right, this is a really important point. And it seems like people who are good at keeping a lot of the details of how their program works in their head at the same time tend to be really good at debugging. And if you're not so good at that, keep a log, because then you can remember more things, because it'll be on paper. Okay, yeah, and don't forget the value of negative correlations. If you try something and the bug doesn't go away, you learn something. It's not in the code that you got rid of, or it's not in the code that's not being run. Okay, so this really helps you to narrow in on things as well. Okay. All right, I think I've beaten that one to death. So the allocator has two major operations. Like I was saying, you allocate a chunk of memory. If it's not available, you return null, and you release a chunk of memory. Okay. So what would happen to the allocator if I decided to just change the release memory part of the allocator to be a no-op? Okay. So you say, hey allocator, free this chunk of memory. And it's like, sure. And then it doesn't do anything. How is that going to behave? What's it going to do? Yeah, memory will fill up. So allocation requests will succeed until you run out of space, right? And then it'll just return null. Okay. That's okay, right? We can live with that. So it says here, yeah. So we can do this. The caller can or should be written in a way such that it expects that allocations could fail. So this, although it's a terrible allocator, you would never want to use this in real life. This gives you an idea of how you might be able to approach allocator bugs. Okay? You disable the deallocate part of your allocator. Rerun your tests. If you have a crash still, what have you learned?
It's not in the deallocator.
Yes. Whatever's causing this crash is not in the deallocator. Have you learned that there are no bugs in the deallocator? No, you haven't learned that. So this is fun. It's like a little mystery game, right? So, yeah. But I mean, you do know that there is a crashing issue in the allocator, if this is the case. Okay. Now, how to disable a piece of the code depends on the language that you're using. So I'm going to give you guys a little bit of detail for C, because that's what you need for CS24. Like I say here, here's a void foo. This is my awesome function that doesn't work. And you do something amazing and buggy, and guess what? It crashes. Okay. Now, you might try to do it this way. Notice you have ABC and then a block comment after it, and you tried to wrap it with comments. This is a very common way that people try to comment out or disable code in C. And unfortunately, this is a pain, because you have to go in here and put a space between this */ so that it's not interpreted as a comment end. Otherwise, the compiler will freak out when it sees the next one, because it doesn't match up nested comment blocks. Okay? So this is not going to work, okay? Unless you go through and you change your end comment blocks. I don't know if some of you encountered that. I've certainly wrestled with this myself many years. So
There's something you can do with the preprocessor.
yes, the preprocessor is a much easier way of doing this. Okay? And this is what I would encourage you to do if you want to try disabling chunks of code. Okay? So notice here we use the if preprocessor directive. If is a very simple one. You give it an expression that can be evaluated at compile time. If it evaluates to non-zero, the code is included in the compiler. Otherwise, if the expression evaluates to 0, then the code will be excluded from the compiler. So in this way, I'm actually turning off the code inside the if and the end if. Okay? Turns out that 0 always evaluates to 0. So that code would just be excluded. So that's a really easy way to try disabling a piece of code and seeing if it's, and if you're not convinced, you could just change it back to if1 and it would include it, and then change it back to if0 if you're not sure, and so forth. Questions? That's a pretty helpful technique. Okay, so yeah, first try, you comment out the release memory code and try the allocator again, and if it still crashes, we talked about this, you know that there's a crashing bug in the allocation code. You cannot conclude that there is not a crashing bug in the dealloc code. And this is another one of those things that's frustrating about bugs, is that sometimes you fix a bug and the program still misbehaves. And the reason why is because there were actually 2 bugs, and the first bug stopped your program before the second one got to run, right? You may see this on the run length encoding problem. Has anybody here tried that problem yet? Ooh, that's a fun one. I really enjoyed putting that together. I hope you guys don't hate me for it. But yeah, you're lucky that you know that there's 4 bugs. And you will notice this, that you fix a bug, and now a new bug shows up. And this is unfortunately the way of buggy programs. Okay. So yeah, you can focus on allocation. Now if it doesn't crash, so let's say that you have your allocator, it's crashing, sorry, let me try to state this. You comment out the deallocation code, and the crash goes away. Now what did you learn?
There's the bug.
Is that the bug? Is that the defect? Is the defect in deallocation? You don't know.
Problem.
Maybe. Yeah, it's a good bet. You could look there. I wouldn't, at least you know that that's where you should probably start investigating, at least as the next step. But yeah, this is one of those things that's a little bit annoying about programming, is that, well, I'll start looking there because that's where I'm seeing the issue. That's the last step in the chain. But I still can't rule out the allocator because it may be that it's just setting up the heap in such a way that the deallocator will crash. Okay? So you have to think like a sleuth. Okay, so yeah, you need to use another strategy to continue that process of tracking down the defect in this program. Okay. What?
Think like
Oh, I don't know. I was going to mention Encyclopedia Brown, but I don't know if anybody here actually read Encyclopedia Brown as a kid. I may be horribly dating myself. Hardy Boys. Anybody read? Yeah. Okay. I'll stop while I'm ahead. So, okay, yeah, so here's another thing that you can do that's very helpful. If you can't chop down the input data and you can't chop down the program itself, there's another thing you can do, which is to create really simple test cases to try to exercise a very specific path through your code. Okay, again, this is where you need to understand the system. Okay? So with the allocator, you could write a program that allocates a chunk of memory and then frees it. I've done this on students' programs as well to see if that crashes. Then, okay, you have a problem right off the bat. Maybe you're not setting up your memory heap properly. Maybe you're mismanaging the first block. Maybe you have a problem in your block split code because the first allocation is almost never the entire memory region. Okay? But if it doesn't crash, well, then you create a slightly more complicated one. You allocate 2 chunks of memory and free the first chunk. Allocate 2 chunks of memory and free the second chunk, and so forth. So you just keep doing this until you can actually reproduce a failure. Okay? Does this sound tedious? It's pretty tedious, but you know what? It's really nice having a program that doesn't suck. Okay? Especially if you're trying to sell it for money. Okay? I guess I'm kind of lucky that I'm in a field where I can write programs with bugs in them and give them to students to figure out. So I'm one of the few people who gets to write bugs on purpose for a living. So yeah, you guys are laughing now, but just wait. Okay, so anyway, you've gotten through step 2. You've isolated it as much as you can, and then let's say that you have it probably down to a function or maybe a group of 10 lines or something like that. And so now you need to study that code and figure out what is it that is actually causing the failure. Okay? And if you find multiple candidates, you need to eliminate them one by one. Okay? So again, you have to be able to reproduce the failure so that you can look at what's going on in each one of those circumstances. Okay? And like I say, if you can't actually see what your program is doing with its state as it executes, you're not going to be able to identify exactly where the bug occurs. Okay? You have to be able to observe the execution, the state of your program as it executes. Okay? Now, I'm going to ask a question. Don't be embarrassed to answer it. Who has never used a debugger? Yay! So, wow, that's really kind of a surprise. How many people have used printout statements in their code to debug problems? Okay, yes, I have 2. That's why my hand is up. Yeah, so there's a couple of different ways that you can actually observe what is going on in your program as it executes. But you have to be able to see how the state is being processed to identify the cause of the defect. Okay, so like I say, you could either instrument your code or you can run your program in a debugger. Actually, both are used professionally. We don't put printf lines in the program. We put logging statements so you can enable and disable, and you can send to rolling log files and stuff like that. We don't just do it the simple way because that's not very maintainable. But yeah, both are used widely, and they both have the same fundamental goal, which is that as the state is changing in your program, at some point it goes wonky, and you want to try to figure out where that point is so you can figure out, okay, saw the state change in the output go bad, and this was the line of code that was executing. So now I know where to look to see what the actual cause of this defect is. Okay. Yeah, and so debuggers are very helpful ways of doing this. They're less intrusive because you don't have to make changes to your code and possibly introduce other bugs, which I have also done. Has anybody here put print statements in their code and added extra bugs when they did that? Wow. Yeah, hey, one person admitted it. You don't know. Yeah. The one that I would run into is I would put print statements into my code, find a bug, and then when I was going through and removing them, I would introduce a bug then. That was always a bad one. So debuggers are much sort of less intrusive ways of doing this kind of thing. Okay, so but I will talk about printing out details so that you can do this, because this is a very common way of doing it. You add print statements to your code, compile and rerun, and you look at what happened. Okay? One issue is that standard output is buffered, okay? Which means that if you have a crashing bug, you can't necessarily guarantee that all the output that you've printed has made it to the console before the program crashed. Okay? This is particularly true if you are printing out debug stuff without new lines, because I think that the console gets flushed on new lines. So people sometimes see this. But when you have a situation like that, the easy solution is to put an flush in your code right after the debug statement to cause it to be forced out to the destination, in this case the console. Flush standard out. So if you do see situations where the debug output doesn't seem to correspond to where it seems to be crashing, see if you may need f-flush statements to force it out. Okay, there's corresponding approaches in Java code and so forth. Okay. I don't know if anybody here has seen this behavior.
Yeah, I've had it in Java.
Yeah, you've had that in Java? Yeah, I've had that in C and in Java when I've been debugging things.
Not in a debugging context.
Oh, okay, yeah. So,
Something I wanted to
yeah, standard out is buffered. Standard error is not buffered, which is why it's sometimes used for debugging and more helpful. Okay, so yeah, if you're going to add debug output, you should probably, when you're adding it, print out everything you can possibly think of. Okay? This is another one. So your program fails. You say, oh, okay, well, this is what I think it might be. And you go in and you add debugging output. You know, you write careful code. And then, guess what? Everything looked fine. Okay, well, I got to go back and do some more. So you have to go back and look and think, okay, what else do I need to print out? And so short circuit this whole process, and just when you go in to figure out a particular section, add all the output that you can possibly imagine needing, so that you have everything you need to identify possible, multiple possible causes, not just one. Okay? I've lived this many times. I don't know if anybody else in here has, but I have been through this more than once. So I just, go for the whole thing. What do they say? Full Monty, right off the bat. Okay. Also, you want to make sure debug output lines are actually unique. Okay. So if you have two lines like this that print out identical output, it's very difficult to figure out what line of output corresponds to what line of code, right? So you always want to make sure, and I mean this may be pretty obvious, but it's surprising what students do when they're tired. And I should say all programmers do when they're tired. So you might as well add some uniqueifier to each line that says, okay, this is line 1 or debug output statement 1, this is debug output statement 2, and so forth, so that you can actually distinguish between them. Okay, so really good idea. So yeah, let's say that you did this all and you think that you've fixed all your bugs. The program is now outputting, it's giving you scroll blindness because it's outputting so much information. And people just do not want to see this. But you may also need that output again in the future. Okay? So what you can do is you can conditionally compile in or out your debugging output. So this is another place that you can use the technique we talked about earlier. Okay? A really easy way, and you'll see this in a lot of the CS24 code, because guess what? It wasn't bug-free when we wrote it the first time. If your code is not bug-free and you get to write 1/10 of the program, then of course ours was not bug-free. We're going to have stuff like this. Pound defines some symbol to be 0 or 1. Okay? And then you set it to 0 to disable debug output. Okay? Yeah, question?
This is more of a semantics thing, but when I do that, the text editor gets all confused about indenting things and all that. So what's the standard? Is it supposed to be all the way to the left or in line with the code?
Something like this? Something like pound define or what?
But
Oh, the preprocessor directives on a line.
If debug, yes.
Yeah, so preprocessor directives are usually always left justified maximally. They're always against the left margin when you do them. Yeah, that tends to be. Now, I don't know if your editor is confused. It may be that your editor sucks. I don't know. But yeah, that's the general mechanism, is that the code is indented as if it were fine, normal, and preprocessor directives are always against the left margin. Yeah. Okay. So yeah, then anywhere you have debug output, you wrap it with an if guard. So something like this, pound if debug info, end if. Okay. And that way you can turn on and turn off your output. Okay. So yeah, this is really nice. I was just thinking, there's a special class of bugs that only show up when all your debugging information is turned off. You do run into those kinds of bugs every once in a while. I've ran into 1 or 2 in my entire programming career. Those are really sad because you turn on the debugger and they go away. And you're like, well, sometimes you'll have bugs that are introduced by the code optimizer in the compiler. Yeah, which make you react like that. And sometimes you have situations where a debug statement actually has side effects that it shouldn't have. So for example, you assert something that has side effects and you don't realize it. And then when you compile it out, the side effect goes away, but you needed it. So those kinds of situations can be pretty bad. Yeah. Okay, so you find the defect, you fix it. Yeah, so we talk about design. I'm going to skip over that just for the sake of time. But you really aren't finished fixing your bug until you've verified it. Okay? You always have to do this last step. We're always surprised at how many times people in CS11 make the fix and turn it in, and then we test it and we're like, wow, not only did the program break, but now it doesn't even compile, okay? Because they didn't actually verify their fix. Okay? And since you should have a way of reproducing the issue, then you should be able to just retry your test case and see that the failure isn't going to occur anymore. Okay? So that's the idea. Yeah, and so like I say, you don't assume that if the fix compiles, the bug is fixed, because that's, yeah, that's like bad programmers do that. That's what Ben Bitdiddle does. Ben Bitdiddle. So there's like these classic programmer, you can sort of think of them as like prototypical programmers, and they have the names Ben Bitdiddle, who you never want to let near any program that's important, because he always does things badly. And then you have Alyssa P. Hacker. And Alyssa P. Hacker is basically, I don't know the word for it, but it's a variant of the phrase a Lisp hacker. So anyway, Alyssa P. Hacker is the good programmer that always does things right. And so that's why in the run length encoding program, Ben Bitdiddle wrote the bad code. Alyssa P. Hacker wrote the test code that saved your butt. Okay. Anyway, so yeah. So bug fixes can introduce new defects, and we call those regressions. We talked about those a little bit. But yeah, usually you have a regression when you don't really understand the cause of the bug that you're trying to fix, or you make a fix that's overly broad and you don't understand all the consequences of it. Okay, so you need to check for regressions as well when you make a fix. And that means test other things besides just the thing you fixed. Okay? Make sure those things still work. Okay? And this is why, again, professional software engineering companies usually have large batteries of tests. And when you make a bug fix, especially as you get close to time to ship your product or release your product onto the internet, you run through this big battery every time you make a bug fix to make sure you haven't introduced new bugs. Okay? And if you fix a bug, you introduce a new test case that verifies that specific bug. Okay, you're lucky you don't have to quite go that far in your classes. But if you decide to do that if you decide to be a professional software engineer, then you'll need to learn that kind of stuff. Okay, final notes to mention. We programmers are very imaginative. I include myself because I learned a lot of these things from myself. Basically, we have a certain way of looking at programs and programming problems and bugs, and we're able to really talk ourselves into thinking that problems are solved or that we understand them when we really don't. And so, first point that I want to bring out is make sure you believe your observations, not your suspicions. Okay. Again, I've run into this. I've heard many stories of others who have run into this kind of thing. You have a scenario where a program fails and the programmer thinks they know what it is, but, and they start to focus on it, but the only problem is none of the signs actually say that that's what it is. Okay? So like I say, there's no indication that the suspected cause is the actual cause. So, yeah, and certainly you can run into situations where you gloss over details that would point you in a different direction than the one you start to follow, and you just don't even see it because you have a hunch, and you're following the hunch as opposed to actually following the observations. Okay? So I want to point this out. Hopefully none of you have run into this yet. You're still young. The other issue is, if you didn't fix it, it's not fixed. Or, I don't know if any of you used Office. Microsoft Office used to have, how they have these tips that pop up when you start the program and things like that? It was like way back, I think it was like Office 97. So again, it was probably way before you guys' time. But there was a particular tip that would sometimes pop up, which a developer from Microsoft added, which said, bugs that magically disappear will often magically reappear. And they added that because that was their experience on working on Office.
Put this in.
There was actually a word tip that would pop up at the start of the program. Yeah. Yeah, so Easter eggs were a lot more popular back then too. So yes, yeah, there's a lot of there's like a Doom simulator in one of them as well. So anyway, so here's another common scenario. You have an intermittent failure. Now notice, it's intermittent. You haven't come up with a reproducible case yet. So it's still occurring intermittently, and you don't really know why. Okay? Let's say you don't have much time. The homework is due, or the product needs to ship. And so you make some stabs at it. You don't really know what's going on. But you definitely can't say, this fix corresponds to the manifestation I'm seeing, right? You can't correlate that. So let's say that it stops occurring after a while. It is appealing to assume I must have fixed it. Okay, that's like saying, I'm a pretty good programmer, and everybody likes to think that. Okay, so and you may even want to avoid testing it because you're like, I just don't want to know. If I don't know, then it's not there, right? It's like Schrodinger's cat. It's like if I don't force the wave function of the bug, it doesn't exist, right? Something like that. So these problems almost always come back. A lot of times they come back in demos or when your TAs are grading your work, things like that. So you definitely need to make sure that you have actually fixed issues. And if you ever have a situation where a fix kind of disappears and you don't know for sure if it's gone, assume that it's not. That's a safe assumption. Okay? Let's see. So the next thing that we're going to talk about, so this was all hopefully just background. I realized when I was putting this together last year, I wanted to put together lectures on GDB and Valgrind, and I was like, wait, people don't know how to actually approach bugs in the first place. So I put together this lecture first. So anyway, all of that is just very general information, and of course it takes a lot of practice to get good at it, sort of discern what parts of your program might be causing issues. So what we're going to focus on next is how to use GDB and Valgrind to debug C programs. So we'll go through that next. I actually have a little example program that I put together. You load some numbers into a list, it prints them out, it reverses the numbers in the list, and then it frees the list. So that's what we'll look at next and how you can use GDB and Valgrind to look at them. And we will record that one as well, so if you've had enough, then I won't be offended. I may be sad, but I won't be offended.